As you all know, one of the key purposes of high-performance computing HPC is to accelerate science and push the limits of science. And given this purpose, it's more than unfortunate that we don't always speak the same language. That is domain scientists and high-performance computing experts and enthusiasts. And domain scientists clearly tend to prefer simple dynamic languages with interactivity, all these high-level features, plotting and whatnot. And on the other end, in high-performance computing, pretty much nothing goes without static compiled languages like C, C++, Fortran, you name it. And given these two different language choices, there is an apparent language barrier between those two domains. And this has many unfortunate consequences. On the one hand, domain scientists lose out on performance that they could perhaps rather easily get, so their codes are running unnecessarily slow. On the other hand, it's also very difficult for them to transition to HPC, to become, HPC enthusiasts or maybe contributors to an HPC library because of that language barrier. And on the other side, HPC might also lose out on, some of the features that these other languages have, interactive HPC as a buzzword, or, maybe there's something to be found there that could be interesting in HPC in itself. And Julia, the Julia programming language that is, aims to solve exactly this two-language problem. So the goal really is to tear down that barrier and establish a gradual transition between domain size and high-performance computing, that you have one language that can be used on both ends. You can use it interactively for your scientific application. You can plot in it. You can do your data analysis in it. But at the same time, the goal is to have a language that can compete with C and Fortran performance-wise on clusters. And what I want to talk about, as nature put it, by the way, Julia come for the syntax and stay for the speed, right? So that's basically the transition from left to right. And I must say that, personally, I'm a physicist by training. I've done that transition myself, right? So I used, or basically I become involved in Julia because it fit my PhD goal in physics. And then, it was one of the reasons I gravitated towards HPC more and more. And what I want to talk about in the next, round about half an hour are the strengths and weaknesses of Julia to give you a basis for deciding whether Julia could be of interest to you. So we'll talk about strengths and weaknesses. And finally, if time permits, I also want to share a few impressions from the Julia HPC community and say a few words about us. All right, so let's start with the strength. And the first point the first statement I want to put out is Julia code can be fast and scalable. It goes without saying that this is a strong requirement if this language wants to have any chance of being used for HPC, right? We have high standards when it comes to performance. We sometimes obsessive. And how does Julia achieve these things? So there, like the story is complex, but the two key ingredients are type inference and compilation via LLVM. So basically, as is custom for dynamic languages, in Julia, you typically don't specify types for your values, and Julia automatically tries to infer the types of everything when you run a function or when it tries to compile a function, that is. And if that's successful, so in the good case, it figured out all the types, and then eventually it has some compiler passes in Julia itself, and finally hands it over to LLVM. So it produces LLVM IR, which LLVM then just compiles to binary code specialized for the hardware at hand. And given this this compilation pipeline, essentially the LLVM pipeline, this basically means that you should expect from good Julia code the same performance as you would expect from any other language like C or Fortran or whatever, if you use a LLVM compiler, which I believe, the default nowadays for most languages. At least, you could compare it to Rust, which is based on LLVM, and I think Clang is also LLVM-based, and NVCC and whatnot. Right, and then eventually in HPC, we also want to make everything scalable, right? We want to use not just one node, but all of these beautiful nodes that we have in our clusters. And the short story here is that Julia has great MPI support. So basically, or for the most part, using MPI in Julia is the same thing as using MPI in Fortran or C or whatever. It calls into the same libraries. So once again, you should expect exactly the same performance there. And having said that, let me at least show some plots, right? That is not just me waving my hand. So the first plot I want to show is a performance plot that I created during my PhD. So this is my determinant quantum Monte Carlo code that I wrote in Julia. So a physics code. And what you see here are, and there were, competitive codes out there already, one written in C++, this greenish line, one in Fortran, the red line, and then my own one. Let's only take the purple one. And the point I want to make here is that, there's a single core, that the single core performance of my code after some tuning was very much in the same ballpark, in that particular case, even outperforming the C and Fortran one. And to give another example that is not by the author of the speaker here, right? It's always great when the speaker shows a plot of his own code that's the fastest. So this is a plot from the Trixie community. So Trixie is a CFD code, which is international, but mostly developed in Germany by Michael Schlottke-Larkemper, ex-HLIS, and Henrik Ranoka, a professor in Mainz. And it's essentially an adaptive higher order numerical solver for conversation laws. So basically, it can do compressible Navier-Stokes equations and so on. And here the topmost line, the orange one, is Fluxo, which is a Fortran code, sort of the thing that Trixie compares itself against. I believe Michael Schlottke-Larkemper has also contributed to Fluxo in the past. And once again, here the story is that the Julia code is very much competitive. And if you look at the blue line, which seems to completely outperform the Fluxo code, the statement here is not that, Julia is much faster than Fortran, of course, but just that, eventually, if you have a fast language that can support high performance, eventually it becomes a matter of effort that you spend on optimizing the code, how smart you are, right? And in that particular case, just more effort has went into optimized Trixie. Regarding the scaling, I also show a plot for Trixie here. So the same code that I just mentioned, scaled across, in this case, 60,000 MPI ranks. I believe this was on Jurica in Jülich. And what you see here is this nice, strong scaling. And yeah, basically just making the point that Julia scales well. There are some intricacies, and we'll get to some of the weaknesses. Also, feel free to ask questions about it later. But eventually, it just ran very nicely. And speaking of scaling, these days, most of the compute of HPC clusters, as you know, lies in GPUs, right? So I also wanted to show the GPU scaling benchmark if you want. And what I show here is the parallel stencil.jl library, which is essentially a framework that allows users to write stencil codes. In that case, so it's a project by ETH Zurich and ZSCS in Switzerland. And basically, they use it mostly for geophysics, multiphysics simulations. And here they just take one implementation that they have once in CUDA-C and once in Julia and scale it up to 1,000 GPUs. I think V100s that was. And once again, the story here is that, you can achieve great performance with Julia here. All right, there are many more examples, but let's leave it at that for the plots. And let's move to the next statement. The next statement is that Julia is interactive and convenient, right? The performance is obviously great when you come from HPC, but in the beginning, in particular young domain scientists, they don't care about performance as much. The first thing you want to get right is that your code runs at all, is bug-free, and so on. And interactivity helps a lot there because you can just iterate quickly. You can try out something, throw it away, try something else, and so on. And this workflow is supported in Julia by the REPL, which is just a terminal-like interface that you can use from the command line. very state-of-the-art, very modern, fun to work with. You have all these other interactive interfaces, Jupyter, Pluto, and whatever. By the way, for those of you who don't know it, in Jupyter, which you probably all know, the Ju stands for Julia. Most people don't know this, so that's why I want to mention it here. Right, apart from these interactive interfaces, Julia has great math support. This is first of all a requirement because most science, numerical science at least, needs heavy math and good linear algebra features, and Julia has all of this. And this shouldn't come as a surprise because Julia has been developed at MIT mainly by numerical mathematicians. So that really shows in the ecosystem, but also in the base language as well. So personal anecdote, when I first fired up Julia during my PhD, when I wrote this quantum Monte Carlo code, it immediately, without me doing anything, knew what a matrix is. I could compute a determinant, right? Basically what you might know from MATLAB, right? You just start it up and it speaks the same language as you, and that felt really, really nice. And the third thing that I want to mention here when it comes to convenience is the package manager, which I would claim is best in class. So basically dependency management, codes depend on libraries and other packages. And Julia has a built-in package manager that just takes care of all of this if you specify what you need. And it's much better to use than the package managers, at least the ones that I know from Python land. All right, let's dive in a little bit into these points. I want to give some HPC-inspired examples of the interactivity and how I have used it, or one could use it, for example, also in teaching. And the first thing I want to mention, since we're in Erlangen, is Liquid. In fact, I want to mention the interactive usage of Liquid, because that's possible in Julia. So Liquid, I assume everyone knows it, but nonetheless is a tool developed in Erlangen. Like I know what I'm doing is the abbreviation standing for, a great name, and it's a hardware performance monitoring tool. So basically it allows you to, on a hardware level, monitor what the CPU core is doing, how many flops it performed, how much memory it has, how much data has went over a certain bus, and so on. So on a hardware level, it allows you to track the performance of your code. And what I'm doing here is I'm using Liquid from within Julia. So Liquid just works nicely with Julia. There was a project by myself and Thomas Gruber from Erlangen. And so what you see here is a notebook, a Pluto notebook. Pluto is very similar to Jupyter. The only difference is that cells know about their dependencies. So if you have the function computation of x that you see here, which adds up the elements of a vector x, it knows if you have another cell that calls this function, then this cell knows that it depends on this function. So if you change the function definition, all the other cells will automatically update without you doing anything. That's the extra ingredient on top of the regular Jupyter interface that you might know. And the point I want to make here is that we define a vector with 10,000 elements and do a computation, as I said, adding up the elements, which is 10,000 flops. And we measure this with Liquid. And what so this will hopefully be an animation in a second. And I hope you can see this now. So I'm changing the computation. I'm adding another multiply, element-wise multiply to it. And we see that the number of flops doubled. And I change it again, and I see 1,000. And this number, now I'm changing the size of the input. Once again, if I double the size, then the flops double, right? And this is not this number, counted flops, which is written there, updates automatically because, once again, due to the reactivity, the Liquid code in the bottom is run automatically. And so I change my function, and Liquid is under the hood measuring what the core is doing. And imagine this for presenting Liquid. I use this in teaching. I would claim this is a much more interactive, much more fun, and more easily accessible experience than using Liquid just from the terminal, from the command line. So this is just one example how you could use Julia for something HPC-like. Another example I want to give is pinning threads interactively. And small anecdote here, both of these packages, like this is threadpinning.jl and the other one was liquid.jl. I essentially wrote, because I attended the node level performance engineering course by Georg and Jan Eitzinger, several years back in Cologne, and I wanted to use Julia, and I couldn't as easily because, there were some rough edges and so on because it wasn't, properly supported. And so, yeah, these packages exist because of you guys. And so what I'm showing here is you can, in Julia, interactively pin your threads. You can just write pin thread sockets to, for example, in a round-robin fashion, pin your threads to sockets. You can visualize in the REPL. You can visualize the system. You see the two CPUs there, and the yellow numbers just show us that we have 64 threads in total, and the first 32 cores of each CPU are occupied by our threads. And then I could, for example, change the pinning. I could change pin thread NUMA and also change the visualization a little bit so that I now see NUMA domains instead of CPUs. And now I see that they are spread out. And once again, I can do this interactively in a session. So I could, pin my threads in one way, run a certain piece of code, benchmark the performance, change the pinning, run it again, and then, for example, learn about the effect of NUMA domains, all within a Jupyter notebook or Pluto notebook or whatever. So this, once again, is great for teaching. I mentioned the package management. So package management is one thing. So it's nice to have reproducible code that you have environment files where you can just, in text form, just write, okay, I need these packages. But apart from reproducibility, that also means portability, because let's say I work on my laptop and I've created my code there and also specified my dependencies. I could just move to an HPC cluster, put the code and the environment there, and write one command in Julia that's instantiate, press enter, and I get all the dependencies that my code needs, the exact versions of the dependencies if I specified them. And this includes binary dependencies. So in this particular case, CUDA would be installed, MKL, MPI, all these binary dependencies. Two comments are in order, I guess, for HPC crowd. One comment is, in Julia, these binary dependencies would be installed one per user. Rather than in Python, it would be one per environment, right? So you would get one MKL per environment. In Julia, you only get one per user, which is arguably better, I'd claim. However, I know that on many systems, you can't just use off-the-shelf MPI implementations. You need vendor MPIs and so on. So Julia explicitly supports system software in a way that you as an HPC admin can just describe in a TOML file that whenever a user adds the MPI.jl package or the MKL.jl package, please use this system software instead. So you can rewire this centrally, and then users won't even notice. They can always override it if it doesn't work, because the local options always take precedence. But this is very nice if, it makes onboarding of people on a cluster so much easier. Array abstractions for easy GPU computing. I at least want to mention a little bit about this. So what you see here is just a basic XPy code. So A times X plus Y, where X and Y are vectors and A is a scalar, and all single precision at this point. So that's this float 32. And then I benchmark the performance on the CPU, which in this case gives me 1.7 milliseconds. And Julia has all kinds of array abstractions, including Q arrays, so CUDA arrays. So what I can do is, the only thing I change is I don't generate a random vector on the CPU or in main memory, but rather on the GPU. So basically, I underlined in red these two changes. And now I benchmark the XPy again. I didn't change the code, and it right away runs on the GPU. You see that the jump from milliseconds to microseconds. And this implementation is, in fact, only smaller than 10% slower than Q+. So it's a very easy mean to just move generic code to the GPU. And you might say that this is an artificial example, right? XPy is pretty basic, and I would agree, but you would be surprised how many codes you can move to the GPU just by using array abstractions, right? For example, deep learning, right? Just a bunch of matrices, matmols, and so on. It's very easy to move them to the GPU. But having said that, you can also write custom CUDA kernels in Julia and even close that gap of 10% to Q+ if you want to. All right. And the last point, the last positive point I want to make about Julia here is Julia invites you to gradually delve deeper. And this is very important because code, it's not just about, what a language can deliver, but also how easily it is accessible, how easy I can look behind the scenes and look what a library is doing and so on. And Julia is great in that regard. First, it's entirely open source, both Julia itself as well as the entire ecosystem. Julia is mostly, to the vast majority, written in Julia. So that means if you want to look how something is implemented in Julia, the code you will see will be Julia code. So once again, think of this language barrier that I showed in the beginning. A curious domain scientist can now just open up a package, a library package, or Julia itself for that matter, and just dive in the code, inspect it on GitHub, right? And see what does this, I don't know, how is the determinant function actually implemented, or which LAPACK function gets called under the hood, and so on. And to make this even easier, so both the source code inspection, but also inspecting the different variants of code transformation that get applied to your code to eventually produce binary code in the end, Julia provides great introspection tools that I want to shine a little bit more light onto. So this is just the tree. So you have your original code, the syntax that you write, and you have macros like which and less and edit, which can show you, where's my function defined. You can even actually open your editor at exactly that position and these fancy shenanigans. You can also look at the LLVM-IR code, for example. You can look at native code, all these different stages. And let's give a concrete example. So what I show here is source code for the most naive Gauss sum function implementation. So just summing up the numbers from 1 to 100, just a for loop, right? And summing everything up. And if I now want to look at what does Julia actually do to this function when I actually call it, and you can spit out the LLVM code, once again, interactively in a REPL, or in a Jupyter notebook, if you will. And in this case, the LLVM code is particularly beautiful, of course, because all of this can be compiled away and just return the answer 5050. So the compiler is very smart in that particular case. And you can also look at the native code if you want. And once again, there are more layers, and I don't have the time to show a lot of them. But I hope that you see also the social potential in this, right? The technical potential, but also the social one. That once again, a curious scientist can become curious about. Okay, what does this vectorized FMA or whatever? What could that be, right? But let's now come to Julia's weaknesses, because there is no free lunch, also not with Julia, right? So let's talk a little bit about this side. The first thing is the obvious, I guess. HPC with Julia is currently a niche, right? So there is, and this has all kinds of consequences. On the one hand, there is limited support by vendors and HPC centers. There is support by vendors and HPC centers, but it's limited. That shows when you want to use tools, HPC tools. For example, Liquid didn't work out of the box perfectly with Julia. I had to write a little wrapper for that. In that case, because we're both NHR, there was a collaboration, but think of other tools by, other centers. Sometimes they work out of the box. Most of the time, at least there's a little effort necessary if someone else hasn't already, written this extra layer. The next thing is few people maintain many core packages, right? I guess that's something you could say about open source in general, right? The bus factor or truck factor. But it's just a sad truth, if you want, that it's way too few people that maintain too many packages. And that obviously has consequences such that there, might not be all features. For example, I said there's great MPI support. We haven't wrapped everything of MPI yet. It's pretty simple. It's typically one-line wrappers, right? Which, by the way, are without overhead. So it's directly injected at the LLVM level. But, we only have two hands and only so much time. So, could be bugs in there as well, right? We all obviously test very thoroughly, but a few people obviously means also limited resources for checking and everything. So eventually, in summary, I guess this just means it's still maturing. It's in a good state, but it's not where we want to have it. And on a more fundamental note, achieving high performance in Julia can be tricky. And the first thing I want to mention here is garbage collection. Obviously, Julia has garbage collection because it's convenient, right? If you think of, once again, this high-level domain scientist who wants a code that just runs, that person probably don't want to, malloc and free manually and so on. So Julia chose to be garbage collected, which also works very nicely. Garbage collection can also be fast. However, sometimes you have to be really careful of what you are doing or know how the garbage collector works to get the best performance. The good news is you can turn it off in Julia. You could just say, come on, for that part of the code, I know what I'm doing. I want to allocate manually. You can do that. Wouldn't be the typical thing to do though. And the two things that, or one particular thing that makes achieving high performance tricky in Julia is type instabilities. I mentioned this type inference mechanism. So basically this code that Julia runs to figure out the types of all the values that are floating around in your code. And sometimes Julia can't figure them out, right? Maybe because you've written bad code, or maybe there's a systematic problem there. But if that happens, this can spoil the performance of your code pretty dramatically. And I'll give a very basic example of that in a second. And the second thing that I encountered when I tried to do real HPC work with Julia was that the task-based multithreading that Julia chooses, which I'll talk about more in 2 or 3 slides, you have to know about it and know what you're doing, because there's an extra layer when it comes to multithreading in Julia. So let's look at these 2 bottom points more closely. So type instability, I'm only showing the very basic concept here, or the most simple example. So I have a type stable function here, which just defines x to be 5, like integer 5, and y to be the square root of x, which would then be a float, and then return y. And I can use the code warn type macro to just let me show the, the type inferred intermediate representation. So you see these annotations here that y has been figured out to be a float 64 because it's the result of the square root function, x is an integer, and so on. This looks all nice. Type inference has worked here. This code would be fast. And let's contrast this with this code, type unstable, where I'm intentionally bad, and I draw at random from the collection 5, 1.2, and 3.0. So this would be an integer 5, a floating point, like double precision 1.2, and a string 3.0. So in the first 2 cases, the function will work. However, it will spit out a different type of result. In the third case, it would even error because square root of 3.0 is not even defined, right? So if I look at this function, by chance, it will either run or throw an error. And if I look at the code warn type here, you see that it highlights in red that it couldn't figure out the types of these things. They are so vastly different that the compiler has given up to make this a union or whatever, but just said, okay, this is anything. And it told me by coloring this red, probably that's not what you want. It will still run, but this can become a performance penalty. And one of your tasks will be to figure out these, find these issues and solve them, if you really care about the performance of that function. All right. Task-based multithreading, I wanted to mention this here. So basically, Julia uses this M over N, or M tasks on N threads model. So basically, you have Julia threads, which are essentially P threads that run on your CPU cores. But then there's this another abstraction layer called Julia tasks. And these tasks in Julia is really what you use when you do parallel computing. So basically, you say spawn a task, right? You probably know this also from other parallel frameworks. And what this means is that if we talked about thread pinning earlier, right? If you want perfect performance in HPC, sometimes you want to tweak it manually. You want to say my threads should be running exactly on these cores, exactly in these NUMA domains or whatever. And you also want to make sure that your Julia tasks run on the threads that you plan to run on, right? So you don't just have to fix this at the right part, but also the left part. And you can do this. You can opt out of this, sort of opt out of this task-based multithreading. You can statically assign where tasks are running, and thread pinning is the tool that I showed earlier, which you can use to pin your threads to cores. But yeah, it takes a little bit getting used to, I would say. And I skipped a little bit over the why. Why would Julia do this, apart from, I don't know, making the HPC folks that want to manually statically assign everything angry, I guess. convenience and composability, right? The great thing about this approach in Julia is that if you hand everything off to a scheduler, like the Julia scheduler, that just schedules everything on the available threads, you can nest multi-threaded code, for example, right? You could have a multi-threaded BLAS library and a multi-threaded user library, and then even user code, which is multi-threaded. And then, everything could be calling each other. And the scheduler would then have the task to, find a halfway decent, efficient scheme for running this on the available Julia threads. By the way, the Julia scheduler is a depth-first scheduler and has been implemented by a person which at that point was working at Intel. So this is one of the cases where we had support from a vendor. Right, and then one more weakness of Julia. Funny enough, it hasn't been a weakness much in my personal Julia ride, but it comes up all the time. And the point I want to phrase it as, or the way I want to put it forward is no easy way to produce small shared libraries. So Julia produces this code, and it is possible to produce shared libraries. So there is a package called Package Compiler, which can do that. But it's not small. The process is not where we want to have it at all. The compilation time of the shared library is way too big, way too long. And yeah, and I don't want to talk about all the intricacies. If you're curious about this, ask me about it. But the point I really want to make is this really, on the one hand, some people say it changes how you deploy your code on a cluster because you don't just have a single binary that you ship around. I never found this to be really problematic in HPC, but what it does, it hampers integration into existing code bases, right? It's not so easy to just take an existing Fortran code and say, here you have a Julia library, you don't have to care that it's written in Julia because eventually you just get a C-callable shared library, right? That would be the dream. It's possible, but it's not easy. Trixie has libtrixie these days to achieve that. But once again, it's one of the weaknesses of Julia these days. All right, let me spend a few more minutes on the Julia HPC community. So as I said, Julia HPC is niche, right? So the Julia HPC community is not very, very big, right? It's small, but it's vibrant and very welcoming. So it's people with passion and drive. It played a lot of a big role also for me personally to dive as deep as I did into Julia and Julia HPC and open source and all the surroundings because it was just infectious and easy. So it's a fun community of people to be around, which I think matters almost as much as at least for me personally as the technical aspects. It's very international. So we have people from pretty much all the big centers. We have from NERSC, from ORNL, from CSCS, from in Germany. I put ourselves there, and so it's small, but we have some big names in that list. And the way I see it, it's an opportunity to join and grow. So the connections to these people are very short. So you can easily get invited to these places, can easily, start collaborations there. So it has potential, right? Nicheness has also potential. And just to give you some quick impressions, right? We always welcome you to one of our sessions. We are present at, Supercomputing, PASC, that was in Davos last summer, or JuliaCon, obviously, our own conference, if you will. These events, both at conferences and also standalone events like workshops and everything, they are very much well regarded, like in the sense that they are always booked out. Once again, on a personal note, I give workshops at least every once in a while, and I've never had a single workshop which wasn't booked out within a week, right? So there is demand for it. So yeah, once again, opportunity to join and grow. And if you can't or don't want to join us at our sessions, we also have a monthly Zoom call, which is open to everyone. You can just hop on the call and, I don't know, share something or just listen, whatever you want. We welcome you with open arms. And let me wrap up. So I talked a little bit about the strength of Julia, that it's interactive, convenient, at the same time fast and scalable, at least if you do it right, which you can learn gradually. It's inclusive. It invites you to gradually delve deeper, which once again is the social aspect that I mentioned. Weakness, it's a maturing niche. Achieving high performance can be tricky. You have to learn about type instabilities and frickle around a little bit sometimes. There's no easy way to produce small shared libraries, and the Julia HPC community is small and welcoming. So the conclusion I want to put forward is Julia has promising potential for HPC, and I invite you to join us in exploring and developing it. And feel free to reach out to me, and I'm happy to take questions.